Alright, this is Mr. Gillum, and today we're going to talk about interior angles of polygons. So we're going to start a new chapter, and we're going to begin with angle measures. So let's take a look here. Some important vocabulary first is a diagonal. And when I say diagonal, what I mean is a segment connecting one vertex to another vertex, but it can't be a consecutive vertex. So in this case, from P to R, that would be a diagonal. This red line here, P to S would be a diagonal. These would be the only two diagonals I could draw from P. P to Q is not a diagonal. Okay, they are consecutive. So this is not a diagonal. Only P to R and P to S would be diagonals, because P to T also would be consecutive. So there's only two diagonals from the vertex P. There's also a diagonal from Q to T and Q to S and from R to T. Okay, so now I have all the diagonals drawn, and they just go from one vertex to another, not including the consecutive connection. All right, so there's diagonals. I just want to remind again of the types of different polygons as well. Polygon that's convex has all angles that are less than 180 degrees, while a concave has an angle that is bigger than 180 degrees. So in this case, this would be a concave polygon because of this angle right here. It's jetting inside. This angle measure right here is more than 180 degrees. As you can see on all of these, they're all less than 180 degrees. So what we're really going to try to look at the relationship in is going to be a convex polygon. So we're going to talk about convex polygons today. All right, and that just means that we don't have any angles that are bigger than 180. So let's take a look here. As far as the angle measure is concerned, there's a way to show this through just drawing on your polygon. We know that a triangle has 180 degrees, and so using that information, if we had a polygon like this guy right here, we could separate it into two triangles. So 180 and 180, that would make 360 degrees for a quadrilateral. And a pentagon, we could connect these to make these diagonals into, looky there, triangles. I have three triangles, so in this case I'd have 540 degrees for a pentagon. And a hexagon, same idea, 1, 2, 3, 4, 180 degrees, 720 degrees. And so if you look here at this pattern, what you should notice is on these convex polygons is that each time we add a vertex, we're adding 180 degrees. And you can see that visually when you draw in those triangles. Okay, you can make these shapes out of triangles if you draw those diagonals in. Okay, so each time it increases by 180 degrees, there must be a pattern here. And so what I want you to look at is this guy right here. Now I think you have a blank chart in there, so I'm going to give you a chance to copy it down here. But as a side number, the number of sides increases, 3 to 4 to 5 to 6. We had the visual of these all the way up to n, whatever n is, however many sides you want to call it, there's a pattern that goes by. And so in a triangle, there's one triangle. In a quadrilateral, there's two. Pentagon, there's 3. Hexagon, there's 4. And that's important because each triangle has 180 degrees. So in this case, the interior angles be 1 times 180, 2 times 180, 3 times 180, 4 times 180, all the way down until you get this equation here. This pattern happens, okay? And so if it's a 15-sided convex polygon, we would have 13 triangles inside, and to find that number of degrees, we would take 13 times 180. Okay, so this is our general formula for the interior angles of a convex polygon. And minus 2 times 180. All right. And so, of course, we have a theorem here. And it says the sum of the interior measures of an inside convex polygon is n minus 2 times 180. That's what we just established. So the measure of angle A plus the measure of angle B, C, D, and E, all those angle measures should equal n minus 2 times 180, where n represents the number of sides. N represents the number of sides. Okay. So let's take a look here. Each interior angle of a polygon is congruent in a regular polygon. So some of these are regular, some of these are not regular. So a regular polygon would be like an equilateral triangle, where each one is exactly 60 degrees. Or a quadrilateral would be a square, or a rectangle, because each one is 90 degrees. Or we'd have a perfect pentagon. Each one of these angles would be exactly the same. Now this chart doesn't quite match what it says with regular polygon. The chart's just kind of added bonus features. So if your word problem say, a heptagon, then you would know it's 7-sided. Or if it says octagon or nongon or decagon, it's just for reference, for vocabulary purposes. Okay, but a regular polygon, when it says regular polygon, that's very important because that means that each angle is congruent. Okay, each angle is congruent. And like I said, this little chart here is just for reference if you get a word problem. Convex polygons. Find the sum of the measures of the interior angles of a convex heptagon. Okay, so right away it says find the sum of the measures of the interior angles of a convex heptagon. So let's just take a look here. We have a heptagon, 7-sided figure. And if it has a 7-sided figure, then we know that it has 7 minus 2, 5 triangles. That's 5 triangles. So my formula that I'm using is n minus 2 times 180, or 7 minus 2 times 180, or in this case 5 times 180. So we'd have 360, 360, 720, 900. 900 degrees. Okay, 900 degrees on the sum of the interior angles would have to add up to 900 degrees. Now it doesn't say anything about being regular, so I don't know that every angle is 900 divided by 7. It just says it's a heptagon, it's convex, and the total measure of its angle should be 900 degrees. In this case, it says find the measure of each interior angle of the quadrilateral. Doesn't say anything about being regular, but it does say it's a quadrilateral, and there's a nice visual here. Okay, so we know already from previous knowledge that quadrilaterals have 360 degrees, but to apply our theorem here, we would know n minus 2 times 180 would be the degrees in a quadrilateral. In this case, we have 4 sides, and 2 times 180 is in fact 360 degrees. All right, now we know that all of these angles together must add up to 360 degrees, so I should be able to solve for x now. I know that x plus 3x plus 90 plus 90 must equal 360. So I just have an equation to solve. And at the end of the day, it looks like x is going to equal 45 degrees. So that tells me that this guy is 45 degrees and this guy is 135. Okay, so I found each measure of the quadrilateral ABCD. All right, so once you have down how much total sum there is in the interior angles, then you can follow along from there and find what you need to find. This time it says the measure of an interior angle of a regular polygon, I'm going to underline that, regular polygon, is 135 degrees. Find the number of sides in the polygon. Measure of an interior angle of a regular polygon is 135. Find the number of sides in the polygon. And so this is a little trickier. It's a little hard to come up with an equation, a good equation. Now being regular, it means that each angle has to be 135 degrees. So let's start with what we know. N minus 2 times 180. That equals the total number of degrees. Okay. However, we know that each angle in this time is 135. So however many sides there are, or how many vertices there are, that's the number times 135 that we're looking for. So didn't explain that very well. This guy represents the total angle measure inside the polygon. Because it's a regular polygon, we know that however many vertices there are, it's that number times 135, because each one is worth 135. And so we can now solve our equation. Again, 180n minus 360 equals 135n. All right. And so I'm going to manipulate this a little bit. I'm going to get all the n's together on the same side of the equation. Now I could choose to factor, or I continue on with my linear equation and get n all by itself. Just keep it simple today. And so when I divide both sides by 45, that makes n equals 8. So in this case, I must have an octagon. So I have an 8-sided figure. One more time, let me explain that again. This represents the total number of degrees in the polygon. The reason I can take 135 times n is because it says it's a regular polygon. Each angle is worth 135 times however many sides there are. So that's where I'm getting my equation from. The total number, and this is the relationship between the 135 and the number of vertices. Okay, and so if I have an 8-sided figure and it's irregular, I must have a regular octagon. All right, that's it for today.